Hello, welcome all to the International Space Federation Think Beyond session. Thank you all for joining. I'm William Brown. I'm a biophysicist at the International Space Federation. So I'm helping the research team here and taking some of the discoveries that are being made in unified physics and taking that to better understand the nature of the biological system. Okay, hold up. I'm seeing. Oh, okay. Somebody just said no sound, but that is probably on their end because I see a follow-up perfect sound. Okay, so yeah, if for some reason uh, you're not hearing me, I appreciate it if you let me know. But yeah, so I am helping the research team here with using the remarkable discoveries that are being made in unified physics to better understand the nature of the biological system. And so that's partly what I'll be sharing with you today. So one of the things I like to do in these Think Beyond sessions is to share research that we're doing right now. So I think in more than a couple of these, what I've shared is not from published papers. It's not polished work. I think it's a little bit more exciting, a little bit more interesting to give you a view inside the lab and share with you some of the things that we're doing right now, some of the work that we're doing in investigations currently. So I actually have quite a bit to get to, so I should probably just start us off, but I am seeing all the wonderful people saying where they're tuning in from, and it looks like we got people coming in from every corner of the globe, all around the world. Australia, Mexico, Geneva, Kuwait, Germany, Oregon. Uh, so great to have you all joining us, and I love the interest in science in general and the interest in our work. Okay, yeah, so I'll just get started here. So, today we're going to be looking at a topic related to consciousness. And this is actually related to some of my, you could almost call it like personal work, work somewhat unrelated to what I do with the team here at ISF. For instance, I have a preprint article, The Volitional Agent Criterion. This paper is actually under review right now in a journal. So it's actually under peer review right now. But it's a paper exploring a definition for the living system. So what is it essentially that defines life? And one of the things that I grabbed to pull up from this manuscript is from Ernst Schrödinger. Ernst Schrödinger was one of the fathers of quantum mechanics. So he is the one who came up with the well-known Schrödinger equation, which describes the wave function of a quantum particle. And he's also somewhat seen as one of the fathers of biophysics because of his work called a book he published, What is Life? And he explored a similar question that I explore in this paper. What is life? What can we understand from the physics side of things that would tell us what is life? But one of the things that he actually says in the concluding discussion of his book is related to determinism, free will, and agency. And he stated that I in the widest meaning of the word, that is to say, every conscious mind that has ever said or felt I, am the person, if any, who controls the motion of atoms according to the laws of nature. And in the paper, I point out that this illustrates two salient points. The state of matter we call alive has, in some cases, undeniably a quality of sentience or awareness. And Schrodinger expressed that the volition of the agent I is in some way coupled to the movement of atoms in the system of the body causing it to move. That at a most basic level, there is the impetus of volition that is the cause of physical motion, like moving one's hand, and hence seemingly controls the motion of atoms, which acknowledges that a key factor animating living, quote unquote, living matter is volitional agency. So that kind of frames one of the key things that I'm going to be sharing here, which is how how your consciousness is causing your body to move. It's signals are coming from the brain and causing, as in Schrodinger's example, your arm to move. What is the origin? What is the source of that signal telling your hand to move? How is that generated within the brain? Because one of the ways that it would be explained as being generated is via like a recurrent loop in the brain. So you have like a recurrent activation pathway that's constantly running, and then somehow that's able to send signals at your volitional intention to cause your body to move. But there's several issues around that if you begin to think deeply into it. What I feel is needed is a way to explain spontaneous signal generation in the brain. So at some point you have the intention, the volition to move your hand, as in Schrodinger's example. So brain cells need to fire an action potential that's an electrical current kind of spontaneously. Uh, how does that happen? I don't know of the biochemistry that would explain that kind of spont what would in molecular and biochemical terms be like a spontaneous signal just generating an action potential. And so one of the things is that I think that the research that we've done recently is answering this question for me. And hopefully I'll be able to share it and it will elucidate this for others as well. So I'll share the idea behind this. So collective network dynamics underlying consciousness. So today I want to explore a neural correlate of consciousness, the synapse, and make a case that consciousness relevant dynamics live at the network scale, and that the story may not be fully captured by spikes and synaptic chemistry alone. Note that I am just saying a correlate of consciousness and that synaptic function is definitively associated with brain processes involving thought, but I'm not making any claims about the emergence of consciousness in the absolute sense. We'll follow a chain of mechanisms that connects nanoscopic organization, especially interfacial water and mitochondrial microstructure, to mesoscale synaptic criticality, and then up into macroscopic hippocampal events, what are called sharp wave ripples. That's a kind of brain spatiotemporal electromagnetic oscillation like the gamma oscillation. But the through line is simple. Biology supplies the energy, but a deeper field layer may be supplying timing, selectivity, and synchrony. So as we move from slide to slide, just kind of keep one question in mind. What physical mechanism could coordinate precise distributed neural timing without needing an explicit electrical conductor for every event? That's what I was talking about with that like recurrent like signal pathway activation, circuit activation in the brain? Is that the electrical conductor that's initiating every event? What I'm asking is what mechanism could trigger an independent signal? How would a spontaneous action potential of a neuron occur, which I believe is the basis of how consciousness intervenes on the brain to form thoughts? So quantum vacuum dynamics and neuronal signaling from interfacial water to presynaptic criticality, a unified field theory of consciousness. We're going to be moving beyond the electrochemical switch, the neuron, the synapse is the electrochemical switch, into a mechanism of robust energy-fed quantum coherence in living tissues. But so why are we talking about the vacuum state of the electromagnetic field? The first reason is that the quantum vacuum is the one dynamic field that is ever present and ubiquitous. It's the background field. It's always there. It's the ground state. In a certain sense, it's the substratum of our world of existence. The second reason is that our unified physics research has revealed how the universe and all the organized matter within it is sourced in the structure and phase relationships of the quantum electromagnetic vacuum. And in previous Think Beyond sessions, I've gone over this kind of hierarchical scale relationship or cross-scale mechanism of uh, coupled harmonic oscillators. And so we can see here a depiction of that. Five nested scales, just to kind of give a metaphorical representation of this scaling factor. And within these five nested scales depicted here, it transduce and amplify one another. At the base level is the Planck scale vacuum, the unified field, if you will, or unified field background. Then, as I've shown in previous presentations, we can follow the cross-scale organization dynamics to the subatomic scale, the atomic scale, and here the nanoscale. We've got the molecular level, for example, interfacial water depicted here, where hydration shells can become ordered and act as like an active dielectric layer within the biological system. Note a dielectric layer is, and this is going to be an important concept here, is where the electromagnetic field is shaped, where resonant electromagnetic modes can be held and structured, and in particular, nanocavities where resonant vacuum modes can be amplified. That's almost like a Casimir-like effect or Purcell-like amplification in light matter interactions. Next, at the microscale, where we can see macromolecular structures like the mitochondria shown here, where cristae geometry, cristae are these folded geometries, this folded architecture, forms microcavities that shape local fields, local electromagnetic fields, and sit near dynamical instabilities. This microscale is nested within the macroscale, shown here with the synaptic bouton, uh, which is packed full of mitochondria in addition to vesicles loaded with neurotransmitters. That's the locus of our focus today. This is an excitable system that can operate near criticality and amplify small perturbations into release avalanches. I have articles on the ISF website, SpaceFed, that describe this kind of property of the brain. It's, near a critical point. So the critical quantum criticality in the brain and avalanche dynamics, these kind of things. Finally, at the macroscopic scale, or one scale up, let's say, I mean, you can see this tissue layer with the naked eye, but at the macroscopic scale, you have like neuronal networks that synchronize like what is seen with gamma oscillations or in hippocampal networks that synchronize into spatiotemporal correlated oscillations. Another focus of today. And the point is not that one scale causes the next in like a simplistic way, but that each scale can provide gain and transduction. So small biases can climb the ladder into observable network events. And so I'm just going to pause for a moment before I get too much into it, because I'm going to check to see if there are any messages, mainly just saying like uh, you're not seeing slides, or you're not hearing me well. So I'm just making sure that there's no technical issues with the presentation. So it looks like, okay, everything is going well. Just kind of in the back of my mind, I wonder if there was an issue, I wouldn't necessarily know until we were all the way through the presentation. Okay, all right. So I'll start this back up. Okay, and thank you. Somebody said all good. So all right, we're on a roll. And so our this is extending our unified physics principles into the biological domain, because from our work, we have shown that mass is trapped vacuum energy, so to speak. You have a proton resonance cavity. It introduces a geometrical configuration, boundary conditions, as well as screening factors that restrict the modes of the quantum vacuum fluctuations and orders them in such a way that there's a certain phase relationship that is highly coherent in the center of the proton and then undergoes decoherence as you go out. But that is the mass, and we can see it in this relationship even here. The quantum vacuum fluctuations within the radius of the proton generate the mass energy density of the proton that's measured experimentally. So our current research is investigating how the same mechanics that organize energy dynamics at the Planck scale, the subatomic and atomic scale, can be operational at the mesoscale of biology. Uh, so I'm kind of modeling a lot of the systems within the cell at the molecular level as nanocavities, bioresonant cavities. And see, um, a key feature of this discovery can loosely be called cavity physics for both. Boundaries filter and reshape the local density of electromagnetic waves, including quantum vacuum fluctuations of the electromagnetic field. We see how that results in mass for the proton resonance cavity. Now, biology is full of nanoscale cavities as well. Membranes, protein pockets, folded cristae of the mitochondria, hydration layers that can, in principle, shape electromagnetic modes and vacuum fluctuations locally, even at like nanoscale areas. We don't need enormous effects. If a system is poised near a bifurcation point with like a critical system, even a tiny bias in local field statistics can shift barrier crossing rates and change macroscopic outcomes. That's the logic we'll apply to synapses and mitochondria here. Nanoscale structures act as cavities that trap, filter, and organize vacuum fluctuations. So it's not just a homogeneous background field. In the biological system, there's symmetry breaking, and there's actually like a unilateral flux to the quantum vacuum energy density. And so that's one of the main thesis that we're developing here. The biological brain functions as an active dielectric vacuum cavity. The zero point field, as our viewers here know, is not speculative. We've got, again, an entire article on the ISF website on SpaceFed about what is zero point energy, what is the zero point field. So it's a rigorously established feature of quantum electrodynamics with empirical signatures like the Casimir effect and the lamp shift. The premise here is that the brain can be treated as an active dielectric element coupled to that quantum electromagnetic vacuum. Now, that was kind of a whole lot of words. And what I was saying there essentially, though, is that the brain is an antenna in the electromagnetic field. The biological system supplies the macroscopic energy budget, metabolism, ionic gradients, vesicle loading, all of that is well established, well known within cellular and molecular biology and neurobiology. But the vacuum's role, so that's classical biology, the vacuum's role, though, is different. It can shape phase statistics, select which modes are favored in a structured environment, and provide extremely precise timing cues to systems sitting near instabilities, quantum timing, if you will. This is the core separation that keeps the model grounded. The energy remains classical for now, while timing and selectivity can, in principle, be influenced by vacuum field structure interacting with biological cavities. So the focus that living tissue can behave like an active dielectric system that is coupled to the electromagnetic vacuum, and that this coupling can bias the timing of key threshold events. This provides a roadmap. It runs from interfacial water polarization to mitochondrial cristae, acting as dielectric microcavities, to stochastic mitochondrial depolarization and calcium transients in the presynapse. I'll explain what that is, to critical vesicle fusion avalanches, and finally to network level synchrony. In other words, we move beyond the neuron as a simple electrochemical switch and treat it as a resonant structure whose phase and timing can be influenced by the background field. And that's a key point in that question. What is the source of that signal? In Schrodinger's example, it tells the hand to move. I believe it is the mitochondria, and that's what we're going to see here. So we need to have kind of a quick overview so that we're all relatively apprised of the system we're talking about here, the synapse. So uh, in the neurobiological model of consciousness, and even just brain function in general, the synapse is the key informational node. It is the junction that regulates neuronal signaling. There's other things like haptic signaling, which is really important, and that's something that is going to be explained if and when we have a paper about this. But the synapse and also junction to junction, like cell connections that also have some regulation in neuronal function. But the star, the MVP player, is the synapse. So for a quick overview of neuronal signaling, you have an electrical current that arrives at the axon, and you can see it in this right there, that uh, action potential as current that arrives at this axon. This is the synaptic cleft. It releases neurotransmitters. Those neurotransmitters are received by the dendrites here, and if there's a strong enough signal, that activates an action potential, which is an electrochemical propagation along this neuron, which has to do with depolarization, which is the movement of large cations, sodium and potassium. And that is the electrical current that goes along to this axon, and the signal is repeated. This process is repeated. But you see, in order for this neuron to fire under this model, it needs an input signal. Uh, so what we're going to look at, though, is when there is no input signal and the neuron fires. Is that a thought? Is that consciousness intervening on the brain to cause a thought? So these are voltage gated channels. So the current causes these channels to open and close, and that's how there's this polarization that's set up. One of the key things in the bouton, the axon terminus here, is that when that current arrives, this is key. It opens this voltage gated calcium channel. Calcium comes into the cell, and then calcium is the signal that tells these vesicles to fuse with the membrane and release neurotransmitters into the synaptic cleft, and they bind to the receptors, and that is the propagation across the synapse of the signal, the electrical current. So first off, what are the limits of this kind of feed-forward electrical model? I've already mentioned one. What about when there's no electrical signal received by the neuron? Can it fire on its own? Is that the source of a thought? So in the kind of the classical view, it's a kind of deterministic linear electrochemical in linear that you have an action potential that comes in, causes calcium influx, vesicles fuse, neurotransmitters are released, receptors are activated, and another signal is propagated. And there's not a whole lot of explanation within that to how that correlates to an experience, a thought, a feeling. There is, however, pretty good mechanism behind how the hardware changes for a memory, and that's important, salient to what we'll be talking about today with what's called long-term potentiation, where you can actually see structural changes in the synapse associated with learning and memory. And that's things like increased actin polymerization, so increased density of the cytoskeleton network in the synapse, and the postsynaptic density. So this is the presynapse, this is the postsynapse, and recruitment of more mitochondria, activation of this really important protein called CAMK2, and increased density of neuronal receptors, decrease of inhibitory receptors. So you can see structural changes associated with learning and memory. But so this is kind of the standard picture, and that explains a lot, especially in terms of like what are the hardware changes that are relevant. But on the right is the reality we have to account for. So synapses behave as metastable, excitable systems with critical dynamics, long-range coordination, and spontaneous events that don't neatly follow the feed-forward script. So, especially when there's feedback, which is an interesting phenomenon. When you see spontaneous release, branching like cascades and network-wide timing phenomenon, it suggests that there's a missing control layer here. And not replacing classical biology, a lot of this is just well established empirically, but fine-tuning it. So in this talk, we'll see how that missing layer is uh, a control layer, a field-mediated timing and selectivity mechanism. One of the anomalous events that we will examine is spontaneous neurotransmitter release and signaling, which is an example of that metastable critical reality of the neuronal synapse. And so with spontaneous synaptic activity, it actually defies the classical model that tries to attribute spontaneous events, spontaneous neuronal activity as noise. Because spontaneous miniature vesicle release, what are called minis, spontaneous action potential independent vesicle release. So neurons will fire without that input signal. And that's called a mini. It's often treated as just kind of unavoidable thermal noise, but there's a deeper problem. Spontaneous activity isn't a nuance, it's not a nuisance that's added on, but rather it's required for synaptic homeostasis, memory consolidation, and for initiating coordinated hippocampal phenomenon like sharp wave ripples. I'll explain a little bit more what they are, but the main point is that they're a high frequency oscillation, um, and they're initiated by stochastic events, one of which are these minis. That's spontaneous action potential independent vesicle release. But they have the signature of a highly coherent, highly coordinated event, highly coherent, highly coordinated signal. Now the information content in ripples can be a true replay of something that previously happened. This has been mapped out in actual animal studies. Or it can be even an imagination of something that might happen in the future. That's also been shown. That is mind intervening on behavior. Now, the anomaly is timing. Thermal noise is random and uncorrelated. It does not naturally orchestrate precise synchronized timing across distributed networks, yet sharp wave ripples are exactly that, structured bursts with coherent timing. So the question becomes, what non-energetic control signal could align timing across many synapses at once? This is where a field-based timing layer becomes attractive, something that biases when thresholds are crossed. And so this activity is occurring in the hippocampus. Hippocampal sharp wave ripples are one of the most compelling empirical anchors for our framework of a quantum vacuum mediated synchronization network layer. Hippocampal CA3 networks generate spontaneous high frequency oscillatory events. These are 150 to 250 hertz, which is higher than most brainwave oscillations. Like the gamma oscillations are around 30 to 80 hertz. Alpha beta oscillations are like 8 to 12 hertz in that range. These oscillatory events, they propagate from CA3 to CA1. Now, an interesting thing about the naming, because I have a feeling that for many people, this is probably the first time they've heard about regions of the hippocampus. But this actually means cornu aminis, CA. That is Ammon's horn, which I think is a very interesting thing because this seems to almost resemble like a horn-like structure. And the hippocampus is right here. It's this structure found in the limbic system that, when sliced in half, looks eerily similar to the Eye of Ra. And so this is the area we're focusing on, where we're looking at the cornu aminis, or the horn of Ammon. And this is an area that's very important to learning, memory, visualization, like imagining things, projection into the future. So I found that kind of interesting coincidence there. But this signal from the CA3 to the CA1 generates the sharp wave ripple, which reactivates potentiated circuits here. The information content in ripples can be a true replay of something that previously happened, important for learning and memory consolidation, or can be an imagination of something that might happen in the future. That is a thought or thinking, and this is the mind intervening on behavior. It is the internal experience that is the key feature of the subjective consciousness. The sharp wave ripples are one of the main phenomena that are observed, but there's also long ripples, which is an interesting phenomenon as well. Um, but the CA3 has kind of extensive recurrent excitatory connections, exactly the kind of densely potentiated network where the proposed mechanism of quantum vacuum bias mitochondrial depolarization would operate most strongly. So the minis, or spontaneous action potential independent vesicle release, are one real biological source of the synaptic stochastic activation, a trigger of short wave ripples. They add a background of tiny excitatory postsynaptic potentials, a small brief voltage bump that makes the inside of the neuron a little less negative, a slight depolarization that nudges neurons up and down in voltage. In a CA3 network that's already near the edge, so it's primed at that kind of critical point, high recurrent excitation or inhibition in the right regime, a small nudge can be enough to push a few cells to spike. Those few spikes can then recruit the recurrent CA3 circuitry and ignite a full sharp wave ripple-like population event. So minis are a possible seed mechanism, one component of the stochastic trigger, which we believe is coordinated via mitochondria, but is that kind of initiation of perhaps a thought, the thinking and the learning that occurs in the hippocampus that's associated with potentiation and memory formation. So in our framework, though, So the minis are acknowledged to be part of the background noise that initiates these kind of seemingly stochastic events that are nevertheless well coordinated, coherent events, collective neuronal action of the neuronal network. But what we're saying here, looking at here is that these minis aren't random across all synapses. They're preferentially occurring at potentiated synapses, where some of those structural changes have occurred that sensitize the synapse that are associated with learning, memory, and thinking. Uh, but that's also where the mitochondria are anchored. And in the potentiated state, they're threshold lowered and ZPF sensitive. That's our primary postulate here. And the timing of those minis is weakly correlated across the ensemble because the 0 point field coupling imposes shared temporal structure and mitochondrial flicker-like events. And that's what's being depicted here. If we look a little bit closer at these mitochondria, they have this mitochondrial calcium uniporter. It's a channel in the membrane, and it's responsible for regulating calcium flux. And indeed, the mitochondria in the presynapse and postsynapse is one of the primary regulators of calcium. Remember that calcium flux is what is triggering vesicle fusion, neurotransmitter release, and the signal to propagate across the synapse. So the mitochondria are a key regulator of this signaling pathway, primarily through this MCU, mitochondrial calcium uniporter. Um, Now, what we're thinking is that the ZPF coupling imposes a shared temporal structure to what are called mitochondrial flicker events, which is a fractal of that mini, which is spontaneous activation of a neuron. There can be spontaneous activation of the mitochondria, the mitochondrial calcium uniporter. It's called a flicker event, and which I'll discuss. This is a potential seed event for minis. So instead of random minis sprinkled uniformly across like 30,000 synapses, so you got these large pyramidal neurons. They can have up to like 10,000 connections in a single neuron. You have a network of them. You're talking like 30,000 synapses. You get temporarily clustered minis concentrated at the synapse of a specific learned ensemble due to this quantum network layer. And the probability of crossing the sharp wave ripple initiation threshold goes up dramatically. Now, a key aspect of this is the role of matrix localized calcium calmodulin dependent protein kinase 2, CAMK2, which regulates mitochondrial calcium uniporter activity. So during learning and memory, synapses are strengthened via a process called synaptic plasticity. You can see that here. When learning has occurred, you get long-term potentiation. That's part of the physical correlate of learning. And it involves many structural changes, actin, microtubules, the cytoskeletal network in the synapse. Importantly, as depicted here, changes in the mitochondria. The mitochondria undergo structural and behavioral changes that correlate with a synapse forming some kind of information retention that it correlates with learning. So this is key within our um, overall thesis that we're developing here. So ZPF, 0 point field bias mitochondrial depolarization, calcium release into presynaptic cytoplasm, spontaneous vesicle fusion causing the mini release, spontaneous signal generation, and then a network amplification mechanism that involves the field, a field-mediated network amplification mechanism. Now, CAMK2, this thing is critically important to brain function. This is the molecule at the heart of brain function and at the heart of most mechanisms that we're looking at. So CAMK2 is the most abundant protein in excitatory synapses and is central to synaptic plasticity, learning, and memory. It is activated by intracellular increases in calcium ion, so it's directly linked to calcium levels, calcium flux, and triggers molecular processes necessary for synaptic plasticity. Like you can see here, this is long-term potentiation being depicted here when this CAMK2 becomes activated via calcium flux. It opens up and it starts binding to cytoskeletal features in the postsynaptic density. This is actin filaments. And the structural rearrangements that are occurring are sensitizing that synapse so that with it has a much lower threshold to activation. It's excitable. So it's a key feature in learning and memory. But so at left, we see a representation of how matrix localized CAMK2 may regulate the mitochondrial calcium uniporter, the calcium channel in mitochondria. Um, I don't know if there's a whole lot more I need to say about that, but this does mean that learning, thought, and internal consciousness processes may increase the sensitivity of mitochondrial flickers. Again, that fractal at a lower scale level, at a lower fractal domain, that fractal of a mini event of a neuron, but it's occurring with the MCU in the mitochondria. And so it might increase the sensitivity of mitochondrial flickers to quantum vacuum fluctuation or zero point field mediated activation, and hence so-called spontaneous neuronal action potentials, which in our framework are not spontaneous at all, but are directed by the action of the zero point field. That is the actual reservoir and medium of the mind. So the framework predicts the following sequence, essentially. High affinity uh, calcium sensors tune the mitochondria in the synapse, in the presynapse here, the axon. And the CA3 ensemble then has a lower flicker threshold, activation of that mitochondrial calcium transporter channel. This is sensitization that follows learning or thinking. So ZPF biased, zero point field biased, coordinated mitochondrial depolarizations across the ensemble's boutons produce near simultaneous calcium release events. Coincident spontaneous vesicle fusion at multiple synapses of the ensemble produce summed miniature excitatory postsynaptic potential spike coupling that cross the threshold for postsynaptic action potential generation. So that the resulting action potentials propagate through the recurrent CA3 network. That's our recurrent seed bursts here, amplified by standard network dynamics, producing that sharp wave. Then high frequency ripple oscillations emerge from the interplay of excitation and inhibition during the sharp wave event. That's the sharp wave ripple. But our prediction would be that the statistical properties of the sharp wave ripple initiation, inter-event intervals, correlation with metabolic state, sensitivity to manipulations that alter interfacial water dynamics should match predictions from ZPF biased mitochondrial dynamics better than from purely thermal stochastic models. So we should be able to measure directly the likelihood that these kind of events are purely stochastic under certain conditions, or whether there is potentially a bias which would tilt a stochastic event from like a 50-50 type Bell type distribution to something that seems to be more directed. That would be our prediction. So that would be the bridge from a subtle bias to a classical synaptic event. if ZPF coupling slightly shifts the barrier crossing rate for a spontaneous mitochondrial depolarization via like the MCU or even the mitochondrial permeability transition pore and these flicker events in the transmembrane channels. Then you get localized transient calcium release into the presynaptic cytoplasm, and then high affinity sensors for those neurotransmitter bound, containing vesicles. So like a high affinity calcium sensor like synaptogamin 7, it's activated. It responds in a highly nonlinear cooperative way to the nanomolar scale, increasing the calcium flux from the mitochondria. It was activated by ZPF coupling. And then a small shift in the statistics of mitochondrial flickers can produce a large shift in vesicle fusion probability. So this is the vesicle fusion with the membrane, and that's going to release the neurotransmitters into the synaptic cleft and activate the corresponding or adjacent neuron, dendrite. So the key result on the slide here, a massive increase in spontaneous vesicle fusion probability without an upstream action potential. This is the kind of mechanism that can turn timing bias into event initiation. So this is the hypothesis I'm exploring to answer Ernst Schrodinger's question. How is it that mind intervenes on matter to cause the movement? Zero-point field, quantum events, light matter coupling, and activation via the mitochondria. So the mitochondrial cristae architecture forms functional dielectric cavities. So this is how we're getting quantum vacuum coupling to the mitochondria so that this quantum field can form this network layer, this timing layer. And so in that way, the mitochondrial becomes a key transducer. The inner mitochondrial membrane operates near a dynamic instability threshold and supports very strong standing electric fields on the order of 30 million volts per meter. That is a lightning bolt. That's the field strength, electric field strength of a lightning bolt. It's inside your mitochondria, 30 million volts per meter. This is very much non-trivial. So you've got within the neurons in your brain thousands or even more of these mitochondria, and within these dielectric microcavities are 30 million volts per meter, like a little contained lightning bolt. Cristae folding creates alternating layers of the low dielectric permittivity membrane and high permittivity aqueous channels, ordered interfacial water, which I'll get to because this is a key part. And with the key characteristics of about 10 to 20 nanometers and thickness, exactly the kind of geometry that can behave like a dielectric microcavity, potentially. Such cavities modify the electromagnetic local density of states, especially for the quantum vacuum modes, which means they can reshape how fluctuations couple into molecular transitions. ZPF coupling, the quantum field coupled to molecular events, biochemical signaling. This might be the key. The slide proposes a per cell-like enhancement factor of roughly 1.5 to 3 in the terahertz regime, overlapping protein conformational transitions and water librational modes, which is like water spinning. In short, mitochondria are not just power plants, their geometry may make them field-sensitive timing elements. And in a very real sense, almost like the brain of the cell. And the interfacial water transduces that vacuum bias via polarization gain. So the water is going to be critical in how the zero-point field is able to couple to matter in the physical in the biological system. Water at molecular interfaces is not the same as bulk water. Near membranes and proteins, hydrogen bond networks can become stabilized and partially oriented. That matters because an oriented dipolar network can act as a polarization gain medium. The polarization that can occur where the water molecules become aligned has almost like a feedback. So it becomes a polarization gain medium. Small bias can be cooperatively amplified into a stronger dielectric or a stronger local electric field. And I've got some math in here, but these are just kind of general math equations. This is showing like the degree of polarization of the interfacial water. Now, because none of this is published yet, these aren't specific equations. This is just kind of like a general equation you could use to quantify the amount of polarization in the polarization gain medium of dynamically ordered water. But as this order parameter pi increases, the hydration layer transitions from a passive bath to an active correlated dielectric medium. We've kind of got one of these microcavities being depicted here. That's going to increase the coupling to the 0 point energy modes that are permitted within this resonance chamber. And so in that way, the interfacial water becomes the first transducer. It converts subtle spectral biases into robust local fields that can reshape gating landscapes in nearby proteins, like the ZPF coupled activation of the MCU, mitochondrial calcium uniporter, the mitochondrial permeability transition pore, biasing, tilting in favor of the event of those flicker events that then cause the mini events. You get directed de novo signaling via the calcium flux. But the seed event, it's the seed event that can kick off a critical avalanche, depicted here. Presynaptic criticality, the avalanche amplifier. We got a vacuum fluctuation that's going to slightly tip that critical point into an action potential. Once vesicle release is viewed as an excitable system, criticality becomes a natural amplifier. So the metaphor on the left is a sand pile. A tiny perturbation can trigger either a small slide or a large avalanche, depending on how close the pile is on the edge, poised at the edge of chaos. And there's just a lot of work now showing that the brain is a critical system. It's at criticality. And on the right, we kind of have a data style picture depicting this, where lambda or fusion intensity showing a burst when the branching ratio is approximately 1. So that's a high probability for an avalanche event. That's the critical state. At criticality, the system is maximally sensitive. Small fluctuations can propagate, recruit additional release sites, and create large coordinated bursts. This is where the model's separation of roles matters. The vacuum doesn't provide the energy for release, metabolism does. The vacuum provides timing and synchrony, nudging a system already poised at the phase boundary. This is how I believe that the field-like nature of the mind causes events. Is it does it in these critical systems that are poised at a phase boundary where all it needs is a little nudge, hardly any quantifiable energy input at all, but it is able to amplify that out into a large scale event because of the nature of these critical systems and their arrangement, like a tipped domino. And so our pre-synapse there operates as a critical avalanche amplifier. And here we're kind of making that phase boundary explicit. When it's subcritical, you get like maybe like little sand avalanches, like small ones going down that sand pile. But when you're at a critical state in approximately 1, a little perturbation causes a large avalanche, a large event. And so, that's in the hypercritical regime. And we believe that could be, generated by a ZPF coupled network state, which can nudge the terminal. And their criticality, that nudge doesn't need to be large. It's just small fluctuations. This is how I believe the quantum electromagnetic field intervenes on neural dynamics via the mitochondria, other systems potentially as well, on the brain to initiate a thought, to imagine, to project into the future, or even to recall the past. But it starts with the ZPF and the neuron acting as antenna. The CAMK2 comes back here because it is a potentiation agent. It's going to respond to those calcium fluxes. I can just point out here that it interacts directly with the mitochondria, the MCU or mitochondrial permeability channel, and so it can actually increase the sensitization of the propensity of mitochondria to have a calcium efflux event, which increases the sensitivity of the presynapse to vesicle fusion, neurotransmitter release. And so if the initiation of spontaneous cognitive events, memories, imagined futures, creative recombinations, the subjective experience of a thought occurring to me is seeded by the electromagnetic quantum vacuum interacting with the brain's CAM-K2 sculpted sensitivity landscape, then cognition is not a closed loop process. It's not that like recurring module, that recurrent circuit that I mentioned at the beginning. It's not a closed loop process like that. It's generated entirely that's generated just entirely within the neuronal network. More so, it's a dialogue between the brain's stored structure and the vacuum field, or background unified field. And so, ZPF synchronization initiates macroscopic sharp wave ripples. And so, we've kind of got the classical biology layer, the slow layer, if you will. And CAMK2, plasticity is going to set kind of the spatial pattern, which cells are sensitized, setting local excitability thresholds, all what has been already correlated with thoughts, with rather learning and memory. But here's our proposed addition to that classical neurobiology model. It's the fast layer, quantum vacuum temporal ZPF waveform. And so this is like what's going to take a whole bunch of minis occurring in the CA3 of the hippocampus and turn it into a coherent high frequency signal. And so the brain in this picture is an instrument. It encodes patterns via plasticity, tunes sensitivity via CAMK2, and which also controls things like cytoskeletal cytoskeleton polymerization, microtubules, actin filaments, and amplify signals via synaptic nonlinearities and recurrent dynamics. But the activation signal, the spark that initiates each spontaneous cognitive event, has its origins in the quantum vacuum. The brain shapes what can be thought, but the field contributes to what is actually thought at any given moment. And I think that's very much in alignment with how we experience learning and thought. And this maps directly onto the broader framework that mind is emergent within the dynamics of the unified field rather than being generated by the brain per se. The brain is the transducer, not the source. And CAMK2 mediated plasticity is the writing mechanism. Experience inscribes patterns onto the synaptic landscape. The ZPF is the reading mechanism that coordinates large scale activity so that you can have something like a thought, a memory that triggers a signal that causes your arm to move. That's Schrodinger's initial query there. And the ZPF is the reading mechanism. Vacuum fluctuations probe that landscape and activate patterns, including novel recombinations that constitute de novo thought. And water is the amplifying mechanism. This is just showing again that order parameter. And if there is zero alignment, if this is zero here, our dipole vector or the sum of our dipole vectors of the water molecules. If this is zero, it's disordered. It's bulk water. Your the normal classical conception of water. But when this is tilted, uh, and your order parameter becomes greater than zero, meaning that there's alignment of these dipole moments of the water, it becomes phase locked, and it's that active dielectric medium that increases the potential to couple to the quantum vacuum. So water is playing a very significant role in this process. And when that order parameter increases and there's water becomes a polarized, dynamically ordered medium, the local dielectric properties change, local electric fields become stronger, molecular conformations can be biased, like with our MCU, the mitochondrial calcium uniporter, and the region behaves like a cooperative polarization medium. This is a key thing we're looking at, and right now we're describing very rigorously the mathematics for this, which aren't featured in my exploratory sharing of these kind of concepts here. But water is extremely salient to this entire mechanism because of its role as a feedback polarization gain medium, where it's just it's like a self-reinforcing loop that leads to stronger local field coupling, amplifying the potential of quantum vacuum mediated seed bursts, as sensitizing the cell even further to those mini events. You start with like a weak vacuum bias that slightly favors one phase orientation. That induces a small amount of dipole alignment. Uh, and when you get that dipole alignment, that increases the order parameter pi. A higher pi strengthens the local electric field and increases the effective dielectric response, and it feeds back on itself. The stronger it couples to the field, the more polarization there is. The more polarization there is, the more it couples to the field. This is a key concept. And so the key line at the bottom is important. Gain is not energy injection per se, but it's a distinct selectivity. The hydration layer converts subtle spectral biases into robust conformational biases, so the system becomes more likely to cross specific thresholds at specific times. So that's we're showing the significance, the importance of water and water in the mitochondria more specifically. This also, though, gives us a direct empirical test that we can do because we can change the absorption, the spectral absorption characteristics of the water using heavy water. So, deuterium laden water, which is the heavier isotope of hydrogen. And so because of the potential importance of the water to the vacuum coupling mechanism, we can do a clean perturbation experiment. And our prediction is pretty simple. Replacing H2O with D2O shifts the vibrational frequency spectrum of water. That changes the dielectric response function in the terahertz regime without directly changing the ionic concentrations or metabolic substrates. And if the frequency of spontaneous minis decreases with D2O, an easy thing to do, uh, independent of like viscosity or some other kind of physical chemical change, that supports an electromagnetic vacuum coupling mechanism over purely thermal stochastic models. In other words, by shifting water spectral response, we can selectively perturb the proposed coupling pathway. And it's the kind of experiment that can falsify or support this proposed mechanism very cleanly. So falsifiable theory. And just to kind of lightly touch on, the that this is we're looking at how this ties in with our kind of historical work on the space memory network. And so, the this is going to lead to changes in the quantum structure of space-time at a fundamental level, and that you know this can be a way that the mind is extended in the quantum field, and memories, which I've discussed in some of my other presentations. For example, at the Science of Consciousness conference last year in Barcelona, I presented a mechanism for how this kind of system that we're looking at here can store permanent information into the structure of space-time, i.e. space memory. So that's a presentation and that's available. Actually, I have an article on the ISF websites, the SpaceFed website, where you can read more about that. We're also looking at how neurotransmitters binding in a receptor pocket can have light matter coupling. So this is actually like forming a vacuum dressed vibro-polariton state, and how that can affect the post synapse. So I've been talking about the pre-synapse, how that can affect the post synapse and activation at the receptor site via coupling with the quantum electromagnetic vacuum. Again, this is another one that's testable because it involves the spin state of the neurotransmitter, which is a magnetic property, and there's also isotope physics that can be used to study this with like xenon isotopes. Xenon's anesthetic, but if you have a certain isotope of xenon, which has a different spin state than the canonical version, it has different anesthetic properties. So it seems to interact differently with its binding pocket. So that's something that we're exploring as well. But uh, critically, like this, what we've seen is that the role of the zero-point field to provide phase statistics, large-scale synchronization, and precise temporal initiation or consciousness in this framing is not produced by biology alone, nor just by an abstract quantum field alone, but by continuous active resonance between the two. So the latter we walk through, water, mitochondria, synapses, networks, describes how resonance and timing can be maintained and amplified without violating basic energy constraints. But it reframes the problem of consciousness as a biophysical coordination problem. How does the brain generate coherent timing across scale? And the so-called problem of consciousness is resolved at a certain level because it is the field. And critically, this isn't just a metaphor or interpretation layered on top of the physics. It follows directly from the mechanistic framework. If ZPF biased mitochondrial dynamics initiate sharp wave ripples, and if sharp wave ripples generate both memory replay and novel imagined sequences, which experimental studies have shown it seems to do, or it's correlated with that at least, then the vacuum field is causally implicated in both memory and imagination. So the creative recombination, the generation of genuinely new cognitive content arises from the interaction between the structured sensitivity of the neural network shaped by experience. That's the long-term potentiation that was mentioned more than a couple times, CAM-K2, and the structured fluctuations of the vacuum field shaped by the electromagnetic ground state. Neither alone produces thought, both are required. But we're going from computations, from the neurocomputational paradigm to resonance, phase, synchronization. Neurons are not just electrochemical switches, they are quantum vacuum radios. So I'll kind of close with the framing shift. We treat neurons as if we treat neurons as purely electrochemical switches, a lot of timing and coordination has to be pushed into the vague category of noise or emergence. If we treat neurons as resonant antennas, quantum vacuum radios, then timing, synchrony, and phase locking become natural control variables. The next step is to turn the model into decisive experiments. Heavy water substitution effects is one example. And there's other potential ones, the xenon isotope experiments. But um, the main thing is that we should be able to test this idea. And we're developing some of the rigorous mathematics to describe it more fully. So hopefully that'll be available as a peer-reviewed publication before too long. And so that's how we'll take our theoretical discoveries into quantitative biophysics of consciousness. But we're moving from model of the brain as a digital computer, which I believe is not a great model, to a model of the brain as a resonant antenna tuned to the field of information. Okay, thank you all for bearing with me through that. Let's see what some of the thoughts and questions were that were coming up. All right. Well, it looks like it was well received. And yeah, so kind of dense with information, and I kind of had to move through it quickly because I put too much information in there, so it was a little bit longer than it was supposed to be. So I had to move through it kind of quickly. But this is going to be recorded, and you can view it later. The recording will be available. Actually, this should be uploaded onto the ISF YouTube channels so that this can be viewed anytime. So let's see. Yeah, so what's the overall big picture that a layperson could take away from all of this? And it's the main point is that we can describe the physics, the biophysics of how a thought is formed within the brain. So at this point in time with the classical model, there's no explanation for that. Yeah, I mean, you have plenty of physical correlates like long-term potentiation, the Hebbian mechanism. But if you wanted to answer Schrodinger's question from 80 years ago, what is that? How is it that I have the intention that I want to move my arm and it causes the atoms in my arm to move just from my intention? This is describing that causal linked mechanism. And the way that it offers a solution that conventional neurobiology can't is that it's sourcing that initial intention event with the unified field, the quantum electromagnetic vacuum. Oh, this is great. So somebody said that they read Pollock and his exclusion zone water, so they kind of understand a little bit deeper what I was talking about with water being amplifying polarization. That's one of I think, the key features of why water is our quantum transducer, our intermediary between zero point field dynamics and biology, is that it is a polarizable medium that has this feedback dynamic with the electromagnetic field. And that's one of the next papers that will be coming out where we explain this dynamic rigorously. So, um, I think that that is some of the key points from the feedback that I'm seeing. So, maybe with the next Think Beyond, what I'll do is have a short presentation, like a 30-minute talk on some topic, maybe even revisiting this. We'll look at some of the advancements that have come from it, and then we can open it up for a longer discussion. I'd like to do that. But I'd like to thank you all for joining, and we'll have another Think Beyond session next month. And I believe Dr. Uh, Guamompre will be uh, blessing us with his presence for that one. So that'll be awesome. So, look out for that and that announcement. So, yeah, thank you all. And I'll look forward to the next time we can come together and explore some of these ideas. Bye all.